General Relativity, step by step. Last time I was observing the difficulty of calculating Christoffel symbols, and this, not difficulty, but they're involved and complicated and messy. What I'm going to do is to use it now. What I want to do is to calculate the divergence of a vector field. So here's some coordinates here, just Cartesian coordinates x and y, and I've got a vector field here, so I've got maybe fluid flowing around and it's sort of mucking around like that. And I'm interested in the divergence of this vector field here, which we've got. So what we've got here, if it's a flow of a material flow, you've got a creation in this little point here because everything's flowing out from this point here. And by Gauss's law, we know there's a creation of matter, if you interpret these arrows as a vector field of velocities. So the divergence, if we've got a vector v which equals v of x, the divergence from elementary stuff is written like that, and in Cartesian coordinates we've got di v by di x, we've got the vector v equals u, v and w, and the divergence, I normally write it like this because I guess that's old-fashioned, and that's di u by di x plus di v by di y plus di w by di z, and that's equal, sometimes you write it as div v, but I normally write it as a vector product like that. And I put a little line over my nabla symbol here just to remind me that it's not a vector, it's a vector operator. We'll see other examples of this later on. So what we mean by this, it would be nice if we've got a vector field v in general contravariant form, which is v1e1 plus v2e2 plus v3e3. Well, it's not really good enough just to take di vi by di xi. We need to account for the rate of change of the basis vectors here. So what we really want is v alpha and then a covariant differentiation with respect to index alpha, and then of course it's summed over alpha by the summation convention, and that's what I'm going to call the divergence of vector v equals this. So this works in any coordinate system, or at least it should, and that's going to be di v alpha by di x alpha. That's a superscript, so it's plus Christoffel symbol, let's get this right, times v, and it's summed over, let's say, a beta. That's a beta. We've got an alpha there and an alpha there. Now, at this point, I just want to make the observation that even in the two-dimensional case, even in 2 dimensions, and we haven't even considered curvature yet, even in a 2-dimensional flat surface, this thing here is a pain in the neck. At least it is, or it would be if we had to evaluate them directly. But we've got this wonderful, wonderful, wonderful system that now tells me that the contraction of it, and remember I'm assuming no torsion, so it's symmetrical in its lower indices, equals a half g minus 1 di g by di x beta, where g equals the determinant of the fundamental tensor in your particular coordinate system, which in this case was equal to h squared sec to the 4 theta. All right, so let's just evaluate this thing and we'll see what it's like. So we've got di v alpha by di x alpha plus, I may as well write out the summation sigma over alpha and beta, alpha beta alpha v beta. So it's di v alpha by di x alpha, summed over alpha of course, plus h v h. That's alpha equals h, beta equals h. plus this one's going to be alpha equals h and beta equals theta. Let's get this right. Alpha equals h, theta, theta. Plus alpha equals theta, beta equals h. Do you see how I'm summing over alpha? Alpha is taking all the things it can do, which is h and theta, and beta is summing, is ranging over everything it can range over, which is h and theta. Alpha equals theta, beta equals h, alpha equals theta, v h. That's right. And the last term is, and the last term is going to be blub blub, do v theta. Well, that's quite hard. That's quite hard. Remember how difficult it was for me to extract. Oh, this one's actually 0, as it happens, but some of these other guys are not 0. This is a pain, and you can imagine this is just 2 dimensions. So if I start fooling around with 4 dimensions, and one of them's time, and 3 of them are space, we're going to have, I may as well write it in, alpha equals theta and beta equals theta. We're going to have difficulty. So what I want to do is to use this beautiful formula here. So I'm going to, this is hard. Okay, so let me write out again what I want to do. We've got, let me just write out that again. We've got di v alpha by di x alpha plus Christoffel symbol of the second kind, alpha, alpha beta, v beta. Oh, I've swapped my alphas and betas around, but it doesn't matter. Equals di v alpha by di x alpha, which is relatively straightforward to work out, plus alpha alpha h v h plus alpha alpha theta v theta. Okay? And then I can rewrite this, because these are you see how I'm expanding it over this argument here, but not that one. I'm just leaving that one as an alpha. Yeah? So these are both summed over alpha. So it's di v alpha by di x alpha plus, no, I've forgotten the half, g to the minus 1, h squared sec to the 4 theta. Oh, I'll write it out in full. It's a half g to the minus 1 di g by di h vh plus, no, I'm going to expand it, 1/2 g to the minus 1 di g by di theta v theta equals di v alpha by di x alpha plus 1/2 g minus 1, that was h squared sec to the 4, h squared sec to the 4 theta to the minus 1 times di g dh, di by di h of h squared sec to the 4 theta. Well, it's not quite as nice as I was expecting, but it's a damn sight better. It's a damn sight better than working out these Christoffel symbols, which were an absolute nightmare. We've taken out the half, we've taken out the g minus 1, we've got the di by di h, and that's going to be vh, plus di by di theta of h squared sec to the 4 theta v theta. Now that's not nice, but it's reasonably straightforward. It's not too bad, actually. It's not too bad. It's not too bad. I'm just going to simplify it a little bit more, and then I'll do it. I'll actually evaluate it for a real vector field, a contravariant vector field, in the next screencast. Di v alpha by di x alpha plus 1/2 h to the minus 2 cos to the 4 theta times 2 h sec to the 4 theta times VH plus sec to the 4 h squared 4 sec cubed theta times the differential of sec was sine sec squared, sine theta sec squared theta times v theta, and I'll just neaten it up a tiny bit, equals di v alpha by di x alpha plus 1/2 h to the minus 2 times 2h vh. Why is that? It's because cos is 1 over sec, and they're both power 4s, plus, not taking the factor of 2 out, have I? I've got a 4 there and an h squared. I've got sec to the power 5 here and cos to the power 4. So what have I got left? I've got 1 sec theta. Is that right? Yeah. So I've taken account of that term, and I've got a sine theta here times v theta equals di v alpha by di x alpha. I want you to see how I'm not scared of this. You just got to write it out. You just got to deal with it. Plus, let's multiply that. Well, let's let's multiply the h's out as well. So the halves cancel there. We've got an h to the minus 1 vh plus 2 h's cancel sec theta. I guess I could write that as tan theta times v theta. Bracket. Oops, not sure what happened there. Go like that. Okay, so there it is. That is the expression for the divergence of a vector, a contravariant vector, in h theta coords. There it is. And it's not nice, but it's a damn sight nicer. Remember how hard it was to calculate this thing here? And that's just one of them. We've got 4 terms here to calculate. And so using this nice expression for the contraction of the Christoffel symbol saves me a bunch of time. When you're doing numerical relativity, sometimes you've got the determinant. Actually extracting the elements of the metric tensor. Sometimes you've got them and sometimes you haven't. So in a way, what we're doing is sort of using this contraction formula here. Wherever it is, this formula here, this can save an enormous amount of time well, it certainly saves a lot of time conceptually, and sometimes it can save you a lot of time numerically as well, because it's a lot easier to evaluate the rate of change of a determinant than it is to calculate all the matrix products and all the rest of the rubbish you've got to do to evaluate the Christoffel symbols on their own. Great, I'm going to stop there. Stop.